Imagine a weapon so powerful that it can tear through 60 meters of solid earth and reinforced concrete, equivalent to burying itself beneath a 20-story building before detonating. A single strike capable of collapsing underground fortresses and creating seismic tremors that rival natural earthquakes. This isn't science fiction. This is the GBU-57, and today we're taking you deep inside the engineering marvel that redefined modern warfare. Before we dive into the depths of this incredible technology, make sure you're subscribed to IntelX, your source for cutting-edge military technology, engineering breakdowns, and the stories behind humanity's most advanced innovations. Hit that notification bell so you never miss our next deep dive into the weapons and machines that shape our world. Throughout military history, the challenge has always been the same. How do you strike an enemy who hides beneath layers of steel and stone? How do you reach targets buried so deep underground that conventional weapons merely scratch the surface? The answer came in the form of bunker buster technology, specialized ordnance engineered not to explode on impact but to penetrate first, then destroy from within. Yet even among these specialized weapons, there exists a hierarchy of destructive capability that spans decades of innovation. Let's establish a baseline for comparison. Cast your mind back to the 1970s when engineers first developed the BLU-109, a 2,000-pound penetrator that could punch through approximately 1.8 meters of reinforced concrete. That's roughly 5 feet of fortified material, which at the time seemed extraordinary. This weapon represented a breakthrough in precision warfare, giving military forces the ability to strike hardened targets that were previously considered impenetrable. But warfare evolves, and so do defenses. As nations learn to bury their most critical infrastructure deeper and behind thicker barriers, weapons had to advance in lockstep. Enter the GBU-28, a more sophisticated weapon equipped with laser-guided technology mounted at its forward section. This advancement allowed for unprecedented accuracy, while its enhanced penetration capability reached nearly 6 meters, approximately 20 feet into fortified structures. To put that in perspective, imagine a weapon that could burrow through a 2-story building before releasing its explosive payload. The GBU-28 represented a quantum leap forward in bunker-busting technology. Yet even this remarkable weapon pales in comparison to what came next. The GBU-57, officially designated the Massive Ordnance Penetrator, stands in a class entirely of its own. With the capability to pierce over 60 meters into the earth, reaching depths of approximately 200 feet, this weapon can penetrate as deep as a 20-story building stands tall. Depending on construction and floor heights, we're talking about reaching depths that most people can barely comprehend. The scale of this weapon is staggering. Picture an average human standing beside this mechanical beast. The GBU-57 measures 20.5 feet in length, carefully crafted into a streamlined aerodynamic profile that ensures stability and pinpoint accuracy during its terminal descent. The diameter spans 31.5 inches across, creating a cross-section engineered to minimize resistance while maximizing penetration force. But perhaps most astonishing is its weight. 30,000 pounds of hardened steel and explosive power, which translates to approximately 14,000 kilograms of guided destruction. This isn't just a bomb, it's a kinetic energy projectile that harnesses the fundamental forces of physics, mass, and gravity to achieve what seems impossible. The sheer weight creates enormous kinetic energy as it falls, allowing it to break through barriers that would stop virtually any other conventional weapon. This compact, heavy design transforms the GBU-57 into one of the most effective bunker-busting munitions ever conceived by military engineers. To truly understand this weapon's capabilities, we need to dissect its construction piece by piece, component by component. The body casing represents the foundation of everything, constructed from a hardened ferro-cobalt alloy specifically engineered to withstand the tremendous forces generated upon impact. This isn't ordinary steel. This is a metallurgical achievement designed to remain intact while smashing through layer after layer of reinforced concrete and compacted earth. Here's something remarkable. The body casing alone comprises more than 80% of the bomb's total weight. This massive structural investment serves a critical purpose. It provides the mass necessary to generate sufficient kinetic energy for deep penetration while protecting the internal components from the violent forces of impact. Sealed within this armored shell lies a precisely orchestrated system of components, each serving a vital function in the weapon's deadly mission. At the forward section, we find the nose fuse well, the first component that will encounter the target. These elements connect through a fuse conduit, essentially a reinforced channel running the length of the weapon. Contained within this protective conduit sits the warhead itself, 5,000 pounds of high explosive equivalent to approximately 2,267 kilograms of pure destructive potential. This conduit then links to the tail fuse positioned at the rear, and here's where the engineering becomes truly sophisticated. This tail fuse serves as the main detonator, and its placement is absolutely critical. Unlike conventional bombs that explode on contact, the GBU-57 requires delayed action detonation, allowing the weapon to bury itself completely before releasing its explosive energy. Moving toward the rear section, we encounter the guidance system, the brain that transforms this massive projectile into a precision instrument. Nestled within the tail assembly, an inertial guidance kit works in seamless coordination with a military-grade global positioning system. Together, these technologies ensure that even as the weapon falls through thousands of feet of atmosphere, it remains locked onto its intended target with remarkable accuracy. Supporting these primary systems are several crucial components. An adapter ring facilitates the attachment of the telemetry antenna, which maintains communication and transmits critical data throughout the weapon's flight. An encryption key battery safeguards sensitive operational information from potential interception or compromise. Deeper still within the structure, we find thermal batteries that provide electrical power to all active systems, ensuring the guidance mechanism remains functional throughout the entire engagement sequence. Finally, there are the composite fins, 4 carefully engineered control surfaces positioned at the tail. These aren't static structures, they're dynamic control surfaces connected to internal gears that respond to guidance commands with precision timing. As the weapon falls, these fins continuously adjust, making micro-corrections to keep the trajectory aligned with pinpoint accuracy toward the designated target. To fully appreciate the GBU-57's capabilities, let's examine a smaller bunker buster and understand how size and design philosophy create vastly different weapons. Consider a typical penetrator in the 4,000-pound class. At the forward section, you'll find a laser sensor that provides terminal guidance during the final approach. Just behind this sensor are adjustable fins that provide initial trajectory control. The midsection houses a warhead weighing approximately 650 pounds, filled with tritonal explosive, a carefully formulated mixture combining 80% TNT with 20% aluminum powder. This combination creates an enhanced blast effect compared to pure TNT. At the rear, retractable fins provide aerodynamic stability and control throughout the weapon's flight. Compared to an average person, this smaller penetrator measures approximately 19 feet in length, roughly 5 meters, creating a more compact profile than its massive cousin. The casing, often fabricated from repurposed artillery barrel steel, possesses exceptional strength while maintaining a relatively narrow diameter of 14.5 inches, translating to approximately 37 centimeters. This narrower cross-sectional area serves a specific tactical purpose. By displacing less material, whether earth or concrete, as it penetrates, the weapon can more easily slip between reinforced barriers. The reduced diameter allows it to potentially avoid or slip past steel reinforcement bars and concrete support structures, enabling deeper penetration into buildings and bunkers relative to its size and weight class. Power and precision come at a substantial cost, and understanding the economic investment behind these weapons reveals much about military priorities and technological advancement. The development program for the GBU-57 required an investment estimated between $400 and $500 million. This enormous sum funded years of research, material science breakthroughs, guidance system development, and extensive testing to ensure the weapon could perform under the most demanding conditions. The production cost for each individual unit stands at approximately $3.5 million. While this might seem extraordinary, consider what that investment delivers. A weapon capable of striking targets that were previously considered safe from air attack, potentially eliminating the need for ground invasions and the casualties they entail. By comparison, the GBU-28, the 4,000-pound penetrator with laser guidance, costs approximately $100,000 to $150,000 per unit. Still a significant investment, but notably less than its larger counterpart. Even more modest is the BLU-109, with a per-unit cost ranging from approximately $25,000 to $84,000 for each JDM guidance kit that converts the unguided bomb into a precision weapon. These cost differences reflect not just the size and explosive content, but the sophistication of guidance systems, the specialized materials required for construction, and the manufacturing precision necessary to produce weapons that function flawlessly under extreme conditions. Understanding how the GBU-57 works requires walking through the complete mission sequence from deployment to detonation. Each phase builds upon the last, creating a choreographed sequence of events that transforms potential energy into targeted destruction. The mission begins with a B-2 Spirit, stealth bomber, one of the most advanced aircraft ever constructed, climbing to extreme altitude. This isn't arbitrary. The deployment height is absolutely critical to the weapon's effectiveness. Due to the GBU-57's enormous size and weight, the B-2 can carry only 2 of these weapons within its internal bomb bay compartments. The aircraft maintains stealth characteristics even while carrying this devastating payload, approaching the target area without detection. When the aircraft reaches the designated release point and all conditions align favorably, the weapon separates from the bomber. The deployment itself is a carefully calculated event, taking into account wind conditions, target coordinates, altitude, airspeed, and dozens of other variables that affect trajectory. The bomb is engineered for precision, and that initial release altitude plays a fundamental role in determining the weapon's flight path and ultimate effectiveness. As the weapon begins its descent, sophisticated guidance technology takes command. The GBU-57 carries both GPS receivers and inertial navigation systems, both military-grade, meaning they operate on encrypted frequencies and with accuracy far exceeding civilian GPS technology. These systems work in concert, cross-referencing position data to maintain an accurate understanding of the weapon's location relative to the target. The inertial navigation system tracks acceleration and rotation, allowing the weapon to know its position even if GPS signals were somehow jammed or disrupted. Satellite communication maintains a constant data link, feeding real-time positional information to the weapon's guidance computer. This digital brain processes incoming data at extraordinary speeds, calculating the optimal trajectory and issuing commands to the control surfaces. This is where the engineering becomes truly impressive. All that guidance information flows directly to the 4 lattice pattern fins mounted at the weapon's rear section. These control surfaces aren't fixed. They're mobile, capable of adjusting their angle in real time throughout the entire descent. As the weapon falls under the relentless pull of gravity, these fins continuously move and adjust, correcting the flight path to account for wind drift, air density variations, and any deviation from the intended trajectory. Think of it as a continuous feedback loop. Sense position, compare to target, calculate correction, adjust fins, repeat hundreds of times per second. This adaptive control is absolutely essential because the GBU-57, despite its sophisticated guidance, lacks any form of propulsion. There are no thrusters to fire, no rocket motor to adjust velocity or direction. The weapon relies entirely on gravity for downward motion and on these control fins for lateral adjustment. This is precisely why high-altitude deployment is mandatory. The weapon needs sufficient time and distance during its fall to make all necessary corrections. Released from too low an altitude, there wouldn't be adequate time for the guidance system to perfect the trajectory, potentially resulting in a miss despite all the sophisticated technology on board. The higher the release altitude, the more time the weapon has to refine its course, ensuring it arrives at the target with pinpoint accuracy. Now comes the most dramatic phase, the moment when 30,000 pounds of hardened steel and explosive payload strikes the Earth at terminal velocity. The impact generates tremendous force concentrated through that streamlined nose cone into a relatively small surface area. This is basic physics applied at an extreme scale. Force equals mass times acceleration. And with 14,000 kilograms accelerating to terminal velocity, the force generated is astronomical. The hardened ferro-cobalt alloy casing is designed to withstand this impact without shattering or deforming significantly. As the weapon strikes, it begins displacing material, whether compacted earth, reinforced concrete, or layers of hardened bunker construction. The narrow profile and enormous mass allow it to punch through barriers that would stop conventional weapons dead. Layer by layer, the weapon burrows deeper, its kinetic energy gradually diminishing as it displaces tons of material. The engineering triumph is that the weapon remains structurally intact throughout this violent process. The casing protects the internal components, the explosives, the guidance electronics, the fuse mechanisms, ensuring they remain functional even after smashing through 200 feet of fortified earth and concrete. When the weapon finally comes to rest, buried beneath the equivalent of a 20-story building, it sits precisely where it was intended to be, deep within the target structure, positioned to deliver its payload exactly where it will inflict maximum damage. The final phase is perhaps the most carefully engineered of all. This is where dual redundancy saves the mission. The GBU-57 carries two separate fuse mechanisms, a primary and a backup, because at this level of investment and strategic importance, there can be no single point of failure. The first fuse utilizes G-force sensing technology. Throughout the penetration phase, this fuse monitors the deceleration forces acting on the weapon. When these forces indicate the weapon has completed its penetration and come to rest, the fuse can initiate detonation. The second fuse operates on a time delay principle, calculated during mission planning based on expected penetration depth and target characteristics. This fuse provides a backup timing mechanism that triggers detonation after a predetermined interval. Why place both fuses at the tail section rather than the nose where they might be more traditional? The answer reveals brilliant engineering foresight. During the violent penetration phase, the nose experiences the most extreme forces and the highest risk of damage. By positioning the fuses at the rear, protected by the weapon's entire length and structural mass, engineers ensure these critical components remain intact and functional even after smashing through hundreds of feet of hardened material. When either fuse reaches its triggering condition, 5,000 pounds of high explosive detonate simultaneously in a confined space deep underground. The explosion creates a cavity, generates tremendous pressure waves through the surrounding material, and literally shakes the earth like a localized earthquake. Underground structures collapse inward, support pillars fail, reinforced chambers designed to withstand external attack find themselves destroyed from within, exactly where they're most vulnerable. The surface effect can resemble a seismic event, with structures above potentially settling or collapsing as the underground foundation is compromised. Bunkers that took years to construct and millions to reinforce become tombs in milliseconds. There's a common source of confusion in discussions about American superweapons that we need to address directly: the difference between the Massive Ordnance Penetrator and the mother of all bombs. Both have impressive names, both represent extreme examples of conventional explosive weapons, but their design philosophies and tactical applications are completely different. The mother of all bombs, officially designated the Massive Ordnance Air Blast, sharing the acronym MOAB, weighs approximately 21,600 pounds. This weapon is designed to detonate above ground level, creating an enormous shockwave and blast radius that radiates outward in all directions. The MOAB excels at destroying surface targets across a wide area: troop concentrations, equipment clusters, surface structures. Its explosion sucks oxygen from the surrounding environment, creating pressure waves that can collapse lungs and rupture internal organs even in individuals protected by cover. However, and this is the critical distinction, the MOAB possesses zero penetration capability. It's not designed to burrow. It's not hardened to withstand impact. It's an area denial weapon, not a bunker buster. The Massive Ordnance Penetrator we've been examining throughout this presentation takes the opposite approach. Rather than maximizing surface blast area, it focuses all its energy into vertical penetration. The MOP can bury itself 200 feet underground before detonating, reaching targets that the MOAB could never touch. Even their deployment methods differ radically. While the MOP drops from the B-2 Spirit bomber, the MOAB is so large it requires deployment from a C-130 cargo aircraft using a specialized pallet system. Once released, a parachute extracts the weapon from the cargo bay and it falls under gravity, guided by inertial navigation and GPS before detonating above the target area. To illustrate the tactical difference, on April 13, 2017, United States forces deployed a MOAB against a tunnel complex in eastern Afghanistan. When the weapon detonated, the massive blast wave sucked oxygen from the cave system, collapsing tunnels and neutralizing the target through overpressure and atmospheric displacement rather than penetration and underground detonation. What we've explored today represents the cutting edge of conventional weapons technology, engineering that pushes the boundaries of materials science, guidance systems, and applied physics to create capabilities that would have seemed impossible just decades ago. The GBU-57 Massive Ordnance Penetrator stands as a testament to what human ingenuity can achieve when theoretical physics meets practical engineering. It's a weapon designed not just to destroy, but to reach targets previously considered beyond the reach of air power, fundamentally changing strategic calculations about hardened target vulnerability. From the BLU-109 of the 1970s, capable of penetrating 5 feet, to the modern GBU-57 reaching 200 feet, we've witnessed an evolution in capability that spans multiple generations of technology and represents billions of dollars in research and development. Every component, from the hardened ferro-cobalt casing to the GPS-guided fins, from the tail-mounted redundant fuses to the 5,000-pound warhead, exists as part of a precisely engineered system designed to function flawlessly under the most extreme conditions imaginable. If you found this deep dive into military technology fascinating, you're in the right place. Here at IntelX, we bring you comprehensive breakdowns of the world's most advanced weapon systems, engineering marvels, and the innovations that define modern warfare. We create every piece of content from scratch, researching thoroughly to bring you accurate, engaging, and thought-provoking analysis you won't find anywhere else. Subscribe to IntelX right now and hit that notification bell so you never miss our next investigation into the technology that shapes our world. Drop a comment below and let us know what weapon system or technology you'd like us to analyze next. This has been IntelX, and we'll see you in the next one.